Hi, I'm Logan.
And I'm Giulia, and we're doing a thermodynamic system. The system we analyzed is the box, as we call it, or the atrium in the academic center. We realized that Olin students and professors really aren't comfortable when they go inside, so we've set out to see how we can solve that problem.
So our system has all glass front windows, which is where all of the energy that enters our system comes in. Energy that leaves our system can either leave through conduction through that same front window back into the world, conduction back into the building through the other walls, or through air exchange when either of the doors open to the outside or to the inside of the building.
Yeah. So what we did is we did some background research on, just sun rays. What we did is the atrium is facing directly east, so all in the morning, all the sun rays comes in, so you get full sunlight, and then throughout the day, slightly less as the angle increases. By noon, it's no direct sunlight. We also looked at how at different seasons, the sun comes at different directions and tried to incorporate that in our model, and you see that through the different seasons that we'll show later on in our model.
So in order to implement our model, we established some differential equations, and these are that the energy in is from the sun's insolation through those front windows, and the energy out is through conduction through the wall or the front windows, and that energy can come in through either of those doors opening. So we have an explanation of all these variables and how they fit into our model on our poster. We also have an example plot of what our system is like without any of our proposed solutions. So this is kind of shows a baseline of what the system behaves like on an average day.
Yep, and looking at that graph, you can see that the temperature is above the normal comfortable temperature that you would like to be in. So we took that and said, how can we solve this? And we thought of three solutions. One is a vent that would allow passive airflow in and out of the building. The second one would be a shade, retractable shade that you can adjust various heights, so various amounts of sunlight can come in through different seasons. We stuck with just one distance to make our models a little simplified. The last one is a tint. By doing a tinted window, it would allow less sun rays in. We chose to do an opacity of 0.5, and that allows certain only certain rays in. Our established temperatures for what is everyone like how is everyone comfortable. Room temperature we decided was a good place to be at, so that's 22 degrees Celsius. We allowed a degree on either side to allow us a little buffer and realistic results.
So in order to implement these changes into our model, we kind of had to write some different pieces of code, so those are detailed here on our poster. We also then show the results of these three solutions on our model. So we have a separate graph for each season. Summer, winter, and then fall and spring have similar sun patterns, so we kind of lump those into one. And then for each one, there's a separate plot of the vent, the shade, and the tint, and how that affects the system. So none of them were exactly perfect. You can see in the winter it does get a lot cooler, and that's just because of the energy exchange with the outside. But in all three graphs, the shade is most likely to keep the atrium at a more comfortable temperature. One simplification we made that Giulia mentioned earlier is that the shade is at the same position in each season, and by manipulating that based on the amount of sun you're getting on a particular day, you could get it much closer to the kind of ideal temperature you want that room to be.
And based on what Logan just said, we created a hypothesis graph. This isn't all the exact data, but we thought it would be a good idea, since the shade was the one that fit the comfort zones the best, to establish this and kind of just show a model of what it would do, what different positions would do to the sunlight in.
So for future directions, this is a model, it's not real life, so there are some things that we could tweak to make it more correct to actual reality. One thing is that we were not able to collect data to validate our model. By the time we were ready to collect that data, the weather had kind of turned sour, and since it was rainy and cloudy, we didn't think we'd get kind of the temperatures we expected, since our model was based on a more sunny day. We also think it'd be great to model how different positions of the shade affect the temperature in the atrium based on the season, so that you could determine what the best position for that shade is on a certain day based on how sunny it is.
Yeah, so taking into these variable factors, we can create a much better model, but so far we tried to be as realistic as possible, and we cited some of our sources just to show that we did go out and see what real world data was and to make it as best as we could. Thanks.